Bueno, es un placer tener hoy por fin a Rodrigo Carrasco. Rodrigo tuvo su doctorado en la Universidad de Columbia, si no estoy mal, el año, sí, no sé cuál, el año 2013. Rodrigo es un profesor asociado del Instituto de Ingeniería, bueno, de nuestro Instituto de Ingeniería en Matemática y Computacional y del Departamento de Ingeniería de Sistemas, de Ingeniería Industrial, perdón, industrial. Y también es el director ejecutivo de la Iniciativa de Ciencia de Datos, ¿cierto? Entonces, ¿este centro tiene un nombre específico?
Ese es el nombre que tenemos, realmente.
Iniciativa del Centro de Datos. La investigación de Rodrigo es en cómo manejar la incertidumbre en sistemas.
Optimización combinatorial.
Optimización combinatorial. Y qué es lo que nos va a presentar hoy. Nos va a presentar hoy una aplicación específica de su investigación sobre manejo de energía. Entonces, pues sin más, tenemos un aplauso para darle la bienvenida.
So I switch to English then. Okay, I'll do the presentation in English. If anyone has any questions in Spanish, more than happy to go with them as well. Okay, so I'm going to be talking about this energy storage management, where it's actually it's part of a FONDEF project which is finished, and it's also part of an UMSUD project that we are currently running, where we're connecting a little bit of the forecasting with the prognostic part to actually make decisions when you have uncertainty in generation. So I'm going to show you a little bit of different things we've been working on and the application we have using stochastic optimization to deal with this setting. There you go. Okay. So the idea here will be to give you an idea of what are the difficulties of managing energy when you have storage and you have this uncertainty in generation. Show you how we deal with that using stochastic optimization for that, and also how we move from this typical part where you have first the prediction part and the optimization part to do something together, where you do the prediction and the optimization at the same time. And I'll show you why we wanted to do this and what are the results using that techniques. Okay. So the idea here, the main motivation of this was basically, how solar energy has been an important part, especially in Chile. We have a lot of generation here, and we have a bunch of things that are interesting in this setting. In particular, since power management is an important part of what you want to do with this, but you have this uncertainty in generation, because there are several questions that you want to address in this setting. Many countries have some goals in terms of how to put solar into their systems, and how this thing adds flexibility, but also has a cost around it, especially in terms of the variability of generation you get with it. As I said before, Chile has that big spot over there, right there. There is Chile. You see that it's the one with the highest generation capacity in the world. So, of course, for us, it's an important thing that we can do here in the country. So that's one of the things that we were looking at. Just to put some things into perspective, those are what's called plant factors. So if you put some energy into a solar panel and you put the same solar panel in Germany, in Italy, and Chile, that's the percentage you get out of the energy. And the only reason here is because we have this very clean air in the north, not in Santiago. So further north, you have a much better clean air, and you have a higher ratio of radiation you get there. So actually in Chile, it makes sense in many applications to actually have what's called a guiding system for the solar panel, something that's following the sun, which doesn't make a lot of sense for example, in Germany, because it's so low the amount of energy you get, you won't get much, you will spend more money doing the guiding than the extra that you get here. In Chile, if I recall correctly, it goes from 21 to around 30% of plant factor you will be guiding. So it's a lot of improvement with that. So it grows significantly. By 2021, we have already in Chile 3,700 megawatts of solar capacity installed already. And they're actually, if you go to the website of the Ministry of Energy, you will find that there are actually 166 other projects that have been developed in 2022, just this year. So we're going to improve the amount of energy, solar energy we have. Of course, the problem with solar is that.
Sorry, perhaps it's an ignorant question, but when you say 21%, that means it's 21% from the estimates that you have in the previous slide?
No, that 25% says that if you get, I'm going to oversimplify it a little bit, but for every watt of solar radiation that gets into the solar panel, 21% of that you will transform into electrical energy.
Like the wire.
Yeah, okay. That you get into the wire. That, I'm oversimplifying, but that's basically it. The ratios are going to be the important thing, right? If you go to Germany, it's going to be only 7%. Okay, so the other thing is, well, you have this problem that one of the main moments where you want to use electricity is when you don't have sun, right? You want to turn on the lights. And that's an important issue there. You won't be able to generate anything at that time. So of course, one of the things that could solve this problem is actually having some storage, right? Of course, storage right now is a little bit out of the question because of its cost. But as you can see over there, prices are going down really steeply. All this electromobility part has improved the number of plants that are working with this sort of things. So the cost has been going down significantly. And today is not just storage is not just seen as something that you would put for resilience, something that you just use as a UPS, for example, for your computer. Now people are thinking of it as a system that you can actually use for sending energy into the system during normal operation. So it's going into that range right now. So that is an important thing. But the problem is now that when you add storage into this, you add extra questions of how to use that storage. And that's the thing that we're thinking of. And in the case, in the particular setting we're looking at is distributed generation, where you have microgrids. You have a small grid with maybe one house, maybe a couple of houses. You have their generation, and you have some storage on how to store the energy and move around things a little bit. So it's a small system. It's not a huge integrated thing, but you have some connection with the main grid. So you have a small thing with storage with variable generation, not just variable, intermittent generation as well, which is solar. So, solar is considered the two things. You have variability during the day, and you also have this intermittence, right? Something that cloud goes by and stop having energy. So it's not just it varies throughout the day, but it also has intermittence. Okay. And the idea of this grid is to satisfy the local demand of this small thing, using the grid as a backup, right? So if you not have enough energy, you will get it from there. If you have too much energy, maybe you can send it there and sell it. That's something you actually can do here in Chile right now, since 2012, if I recall correctly. You're able now with the net billing, the law that we had at the time, you can actually sell your excess of energy with certain limits in capacity. You'll be able to do that. So in our case, we're going to be talking about a photovoltaic solar grid, microgrid. So your generation is going to be based on solar panels, and you will have some sort of storage, maybe lithium batteries, lead batteries, or something like that. So we'll have that as a system that will allow us to give quick response. Batteries are really fast to give you and store energy. So we'll have that. Okay, so what happens when you don't have storage, right? If you don't have storage, basically the decision is pretty easy, right? If you have enough energy, you give it to your whatever demand you have. If you don't have enough, you'll have to get something from the network, right? And if you have more than enough, you can send it there. That's basically all your decisions. There's nothing more you can do about it. The moment you have storage in the system, now the questions start to complicate a little bit, because now if I have some extra energy, what should I do with it? Should I store it? Should I sell it to the system? And furthermore, if I have some sort of information about what will happen tomorrow is going to be a really cloudy day. Well, maybe it makes sense to actually store more today and not actually use it most of the day, because I'm going to be using it tomorrow. Maybe my demand, the load I'm going to be serving with this energy, it's going to need that amount of energy in the afternoon. So I'll store this the whole day and use it tomorrow. So those type of questions start appearing. When should I store? When should I sell? Should I sell the energy I have in the battery? You also have some sort of losses within the battery. It's not a perfect system, so you have losses throughout the day. You have also a loss between putting energy into the system and getting it out. You also have a loss there. So it don't make sense or not to actually do it. So that's the question that we try to address with this. And the idea was to develop a model for this small PV microgrid. include the storage capacity, see how we're going to deal with it, and somehow deal with the stochasticity of having variable energy and having variable demand as well inside. How can we make good decisions in terms of what to do with the energy to maximize the benefit, the economical benefits for whoever is using this? Basically, we're trying to minimize costs in this case, and use all the energy and make sure that the demand is always satisfied. So that's going to be our main constraint. Any questions so far? Good. So they told me that, I'll go a little bit into the background of what stochastic optimization is, in case somebody doesn't know that. Basically, the idea in this case, we're going to be first dealing with this as a two-stage stochastic optimization, right? So what we're going to do is, okay, we have a first stage decision, that's that C over there, right? And there's something that we do afterwards, that's something that happens afterwards. There's some realization of this uncertainty afterwards, and we have to deal with that afterwards. How we do that? So this is if you study stochastic optimization at some point, there's a very nice problem that's called the farmer's problem. I don't know if you know it. Basically, the problem is saying, you know what? Think of the farmer that has a piece of land. He or she wants to plant certain types of products, but he or she doesn't know actually what's going to be the yield of each of the different areas, right? So what decision you take first, given that you have some requirements afterwards for whatever crops you're planting. So your first decision is going to be, how much of this area I'm going to be planting on different types of plants, right? And then my second stage decision, once the realization occurs, right? Things grow, you have certain amount of tons of the different products you actually get from the land. Then you have to, decide something. Maybe you have more than you thought, and you will have to go and sell it. Maybe you have less, and you have to go to the market and buy it, right? So that's going to be your second stage decision. So that's basically the setting we want to use that, and try to see how can we actually put this problem into that setting. So this is a little picture of what we have. The yellow lines here represent things that are uncertain. The blue ones are things that are certain, right? So I don't know how much sun I'm going to get. So that's going to be my generation. It's uncertain. That's going to be my demand. I don't know, how people are going to be using the electricity throughout the day. So those are my main sources of uncertainty. But if I want to buy or sell anything from the grid, maybe I know how much I can get it, or maybe I have some information about what the battery is going to have. So I have information about how much to get in or out of that. Yeah. So the first thing we said is, well, let's try to simplify the difficulty of this. Let's go with that. And let's change a house for maybe a farm, right? In farms, it's pretty easy to predict the demand. Basically, most of the things are like pumps. When pumps turn on, turn off. So that's a fairly easy thing to deal with. So now you have your demand, some more known one. I'll show you at the end, what we do with the other setting, which was the one that we were interested in. But for the time being, let's say, I know the demand. So I have this curves, nice curves there. Well, still I have all this yellow arrows over there. And I would love to have that, right? But if I do that, and I say, I'm going to get this amount of energy from the solar panel, here's an equation that's not going to balance, right? Because I have this yellow thing coming in that can be uncertain, and I have the other ones out. So what we said is like, what if we cheat a little bit and we think of this solar panel and the grid as a single thing, right? So we do the balancing by thinking of our second stage, or maybe our second stage being the things that we can balance with the grid. So we sort of create that. So that's going to be sort of the idea there. So our first stage decision is going to say, you know what, I think I'm going to create this amount of energy from the solar panel, so I'm going to decide everything. And if I screw up, I'll fix it by buying or selling energy from the grid. So that's going to be my second stage decision. And that will deal with this, a certain part over here in yellow. Okay, that allows us a little bit to simplify a little bit the setting. It's not that far away from what we have, but allows us to separate this and make it into a two-stage problem. Maybe help us deal with the difficulty. Yep.
From an economic perspective, the grid doesn't have variable prices. Like, I don't know, in the night, it's in the day it's cheaper, the energy, or the night it's not. I don't know. That part could be like stochastic also.
Sure, that's a very good question. Actually, in this case, we are including the fact that prices can vary throughout the day, but are known. So you can add it into the system. We have to think a little bit on if our current setting can just deal with it. We're still using variable prices. In Chile, you can have that. There's a flex type of the Enel has it, that you have some sort of cost from 6 in the morning or 7 in the morning until 10 p.m. I think it is. And then it goes up 30% from 10 p.m. Oh, no, sorry, from 6 p.m. to 10 p.m. And then it goes down 30% from 10 p.m. to 6 in the morning. So, I mean, I had it in my previous apartment, and I could tune the washing machine, for example, to do the washing at night, and I got some savings from just doing that, shifting around the load. So we're considering a variable price, but it's not a stochastic price, so it's known beforehand. Any other questions? Okay, so that's going to be my setting. If that's the case, then my first state decision is going to be, what are the flows from the panel to the demand, from the battery to the demand, from the network to the demand. I'm also have as first stage decision, the panel to the network and the battery to the network, and what's going to be doing my storage, how much energy is going to go out. And the other reason I wanted to do this, it's also because I have one variable inside here, right, that depends on everything in the back, right? So we have that problem there, which is this guy here, right? This one is not, the amount of energy I have in the battery is not just something I know in time t, it will depend on everything before that, and it will affect the decisions in the future, right?
You said that now we are just in two-stage model, and then t is either 0 or 1, or?
T is gonna be, in this case, I'm gonna write in stone everything I'm gonna do tomorrow. Yeah, from 0 to 24, let's say every hour. And we're doing it every 30 minutes. So I have 48 time steps. I'm gonna write everything there. And that's what I'm gonna do tomorrow throughout the day. And then I'll try to fix it by doing it at every time step. I'm gonna be fixing it by buying and selling to the network, whatever I didn't got from the panels. Okay, I'm gonna be fixing that in the second step.
But then it's a multi-stage.
No, I'm not saying it as a multi-stage yet, because I'm saying I'm writing the whole day from the start to end as my first day. So this is the things I'm gonna be doing the whole day. I write it in stone, and the only time I can do anything else is gonna be tomorrow at midnight, once everything already passed. So my second stage is sort of a dynamic second stage in the sense that every hour I'm gonna be buying and selling throughout the day, but I see that as a whole just second stage. And since I'm not, that's the reason I want to do this, since I'm not touching this guy with the yellow lines, then my state of the battery is not going to change throughout the day. So whatever I wrote that's going to happen is going to happen. So that's the trick, the modeling trick we did for dealing with this. Okay, so additional things that we were asking, right? You can have variable prices throughout the day. You have some selling price, you have a buying price, you have a maximum capacity of the battery, you have some sort of capacity of flow inside and outside of the battery. So you also have the limits. So you have those sort of things. And my second stage, as I said, we'll have this generation is going to be stochastic. And my second stage will have a deficit or a surplus of energy that I'm going to be dealing with by connecting it to the network. That's going to be my for each scenario you might think of happening tomorrow. I'll be doing these sort of things with the network, which is a sort of an infinite amount of energy I can get or put in there within the context of what I have as a microgrid. Okay, so pretty easy equations. If you see the model as a DC model, it's called, right? So we see everything as a simple DC model. Since we have a small microgrid, you don't need to deal with the Kirchhoff laws and all those sort of things that you need when you do alternate current models. So you have that from the demand point of view. You want to make sure that whatever you get from the panel, from the grid, or from the batteries satisfies your demand. This is going to give us, how much energy we can put into the batteries. That's going to be limited by whatever the rate that you can charge the battery. Whatever rate you can uncharge the battery, you can get energy out of it, right? So it also has a limit. We'll have the battery, how it moves throughout the day, and you'll have all this little coefficients that represent, how much energy you lose from one day to another one. Also, the efficiency of the battery in terms of how much energy you put inside and you get out of it, right? And you have the limit in terms of how much capacity that the battery has. Pretty simple model. If you think of those tricks I showed you before, now the model is relatively simple until we get to this equation, right? Where we say, okay, I want to make sure that all these flows somehow are linked with this thing here, right? So I create these two second stage variables, our z's that are there from this surplus, and I use those as a measure to deal with this different scenario. So I'm going to divide the world in different scenarios that you have as a second stage, right? Which is now, that's why I have a S on top. And that will tell me, one of the millions of scenarios I might have of solar energy tomorrow. Remember, for me, a scenario is the whole day of generation. It's not going to be just 1 hour. It's actually the whole curve of that generation for the whole day. So I can have thousands of those, right? And this thing is going to be balancing in the second stage by using those Z's over there. Okay, and that's going to be my cost function. There I have the variable cost that you were asking for, right? It's going to be up there. So we have a variable price, maybe a variable selling price also could be there. And since I want to minimize some sort of expected cost, I'm going to just give some probability to each of the different scenarios and just multiply that by the cost. And that would give me the expected value of this thing. Okay, so we have to deal a little bit with some penalization, a little bit of things you need to, I'm hiding under the carpet right here to make sure that, multiple solutions are condensed into just one, some technical things that we can talk afterwards if you want to know a little bit, but the general idea of the model is the other one I showed before. How do we create those scenarios? So in the general sense, we want to have for each of these curves of generation that we have, right? We're going to have some first stage decisions that when written in stone, we cannot do anything about them. We'll have the world divided into many different scenarios that gives us some curves in terms of generation, and some second stage that kind of deciding, if you have so much sun, you'll do this or that, right? With this second stage variables right there. So you can have a bunch of different scenarios. One way, of course, of doing it is what I said at the beginning, right? You can think of having some historical data and try to use some machine learning tools to build those scenarios. So that's the first idea we had a couple of years ago with some undergrad students. It was Isabel Bebe and Slavia Volkovic. Both of them, they started working on this. So we drafted, I think it was 10 years right there. 10 years of solar data that we got from Chile. And we grabbed that information and started to see if we could cluster things throughout the year. They were using, in this case, K-means, very simple machine learning technique for doing clustering. And what you can see here, for example, is I think it's January, where you can see that at least over there, you had 73% in January of really nice sunny days in Santiago. Then you have a 13% where you have a sort of a morning with a little bit of clouds, and then the rest of the day is going to be sunny, and a very small, 10%, which is just a bunch of different things there that just got into that when we did the clustering. So we can think of that as our clustering and use that as a scenario, which is, first, it's interesting because we went from having 400 and something scenarios of sun into clustering into this little groups, right? So we only have 3 scenarios maybe that we can use. So that's the first thing that was interesting. So it's fairly stable. How the different real data is fairly stable. How you see the sun going from one day to the other. If you try to do this, for example, with wind, it's going to be a different ballgame, right? Because it's much variable throughout the day. If you don't have this curve, right? If the sun doesn't come up one day, you have much more important problems actually dealing with predictions, right? Whatever.
These are the centroids of the clusters.
Sorry? Yeah, sure. What you see is heat map. I put all the different scenarios that were clustered into this in the heat map, and the red line is the centroid of that cluster. So you can think of this as a cluster in R48. We have 48 dots, right? And that red dot is our centroid for that.
My question was where it comes from the 48.
Every 30 minutes.
Okay.
24 hours, every 30 minutes, so we have 48. Why choose that? It's basically because the data came in divided in 48. I mean, we could divide in the middle and try to use more sophisticated things in the middle, but we didn't think it was, since it's so stable, we don't think it was needed to do anything else. If you went with wind, for example, where things can blow out, for you say, no pun intended. From 1 minute to another one, then you'll need a much finer time resolution.
Yeah, but go in a higher space, also you pay something.
Sure. It was done, fairly straightforward, not thinking much about it, because you also can simplify this about from midnight to 5 in the morning. It's always going to be a 0. So there's a lot of reasons to have anything else in here. You might think of just concentrating this part. The problem with that is now you have to start thinking, time changes throughout the year, and how much this gets thicker and smaller throughout the year. This was just plug in there, into the machine learning blender and see what happens without a lot of extra processing.
No, I think that's so it seems that you have a lot of dispersion in the clusters that you found. Like scenario 0 seems to be like very scattered and so on. So my question is, does this have an effect when you have to do the simulations, or would you want like clusters that are more concentrated around the centroid, so that you don't have like that much dispersion between scenarios?
Yeah.
Or
of course, I would love to have everything as closer as possible. Now you think here, the problem is that this sort of scenarios is actually very little percentage. It's 10%, 13%. So maybe it's not going to be a big deal. Then we'll see afterwards when we do the analysis after with out of sample examples. So we'll see how much that affects, right? But sure, I would love to have a really good prediction for each of those scenarios. So let's start with a case study, and the first results. So we have we had a simulator with 62 homes in Santiago, a total of 277 kilowatt hours per house, some 250 panels out there, a bunch of information that we use. That's fairly regular for a small size microgrid with a bunch of homes. So you had that, and we use that as information. We use actually real pricing that you have here in Chile, which is around that, and some information about the lead batteries that are currently in the market. So we use that as a simulator.
So these batteries are per grid or per house?
These batteries are per grid.
Yes.
So it's just a single system for the whole thing.
Yes.
Yeah.
Rodrigo,
Yep.
where these homes were located in Santiago?
We're assuming in Santiago because we're using data from solar relation Santiago, and we're using demand data from Santiago as well.
But in what part of the city?
No, we don't have. This was just simulation part.
Okay, because I was going, I don't know if you want question now or at the end, but I saw some similar study in the UK. But in the UK it's different because people usually use electricity for heating, and also they have standards that is usually quite common, like you want your home at 20 degrees. But in Chile, you have like so many ways to heat your house. And in general here, like people don't have like, I don't know, like central heating, like it's very, very rare. Like people using, I don't know, like gas or paraffin. And also they are used more to like, I don't know, get like a coat inside the home, So that's why I was wondering, like, I think that maybe in the upper part of Santiago or the Sector Oriente, people have some standards that are very different to.
Totally agree. I mean, the main reason I wanted to change that little house I had in my drawing with a farm was basically because of that. I mean, it's much harder to predict what a bunch of people are doing, and I'll show you at the end what's going to happen, right? So right now I know what the demand is going to be. I'm simulating some demands, but I know from beforehand what they are. So I don't have that problem yet. Yeah, but I will have it if I want to just put this in, the house of any of you. I will have actually that problem because I don't know how much you consume energy throughout the day, right? Right now I know what's going to be the demand curve, and I'm going to show you what we did a little bit later in the presentation. Okay, so how do we do a simulator actually for this, right? Because I cannot just grab some information and do random, right, numbers of generation in each different times of the day, right? We need something that's actually connected throughout the day. If it's starting cloudy, that doesn't just turn sunny and then cloudy again. That doesn't happen, right? So we created, I can share with you afterwards the details if you want it, and we have an open source simulator if you want to use it as well. So basically we're using copulas to actually connect everything at the back and actually have the same marginal distributions of each of the different hours that we see from the data, and they also connected coupled at the back with the same covariance throughout the day. So we have a very nice simulator for the sun generation. So we use that. I'm going to jump on that. And then, we give that to a model, we simulate many things, and we start getting results from this. Here you can see an example of one day. I'll show you afterwards the simulation of many days for different times of the year. And you can see here that in cyan, I guess, I barely see three colors, but I guess it's a sort of a cyan color there. And you can see that a line that's giving you the demand. And then in colors at the bottom, I show you where the energy is coming from, right? So the red one comes from the network, the blue one comes from the battery, and the green one comes from the sun. So you can see, of course, when the sun comes out, right? So you try to put all your demand with that. But when the prices are high, like it's in the afternoon in Chile, right? You will have something getting out of the battery, and the rest of the day you'll be using the grid. One of the funny things about the problem we're dealing with is that once you see the solution, it's pretty obvious that you should be doing that. But before you see the solution, it's not that obvious what you should be doing, right? So of course, now you see it, and it's like, oh, of course I'm doing that, right? But the policies right now, you have to think that the policies that people are using right now, inverters, when you put a solar system in your house, the inverters, they don't do anything like this, right? The inverters, the only thing they do is, if I have extra energy, I'll store it in the battery. If I don't have enough energy, I'll get it from the battery, and that's it. I'm not doing anything more sophisticated than that. So here's some profiles from the battery, how it's going to be throughout the day. And here you have, actually when the energy is really cheap, we see that actually given the parameters we were using, it's actually convenient to load the battery from the grid and have that energy stored throughout the day and use it at certain points. So you see that as well from that, which is pretty obvious afterwards, but you don't know actually what's you can check around and play around with the parameters to see actually what's the breaking point of that. But from beforehand, you don't know actually what's going to be the price that will allow you to say, oh, sure, I'm going to get from the network some energy, store it in the battery, and use it afterwards.
Do you have some image or graph showing when the decision of selling from the solar panel? Because I would expect that the correlation of production in the solar panel on the solar panels is high. So if I'm getting a lot of energy from my panel, so is everyone else. So it wouldn't make much sense to sell at that moment if everyone is getting the demand from the panel. So is there some confirmation of that intuition? Or?
Yes, you're totally right. It depends on several things. One is actually the storage size. If you have very little storage, well, you have to do something with energy instead of throwing it away. Even they give you really low amount of payment for that. Well, the other option is zero, right? So it gives you. So you have a larger, say, storage system. You will always prioritize storage over that. In the case of Chile, actually, given that the price of selling is so low compared to the price of buying, you will never, unless you really have your storage completely full, you will never use it as a seller to sell your energy. So it actually confirms those type of intuitions we have right now here in Chile. You confirm it the same one.
The state of the battery at the end of the day, it's zero always?
Very good question. Yeah, sure. Right now, I also hit on the rug, right? I said, I'm doing this every day. So of course, I don't have any benefit of storing anything here. Since I'm doing that every day, sure, it always ends up in zero. If you do this and you can simulate, like several days, and you do a multi-stage model with this, thinking of each stage as a day, you don't see this, right? It will end up over here, and then you have the same cycle over there. The only difference between having a multiple stage one and a simple stage one, two-stage one, is going to be this ending part here. So you end up with zero because there's no reason to store any energy. I'm going to start from scratch tomorrow anyway. But if you do a multi-stage model, you'll end up something in the middle, and it will just be something like this, and then we'll repeat day after day after day.
The complexity of that is.
Yeah,
pretty high, or-
the problem is that you start paying with that complexity. We moved into that domain. I'm showing you at the end, what we did with that. So you start to think of the composition algorithm to actually solve this. This is basically solving big LP. We grabbed the LP stochastic optimization problem. We just wrote it a huge LP, sent it to Gurovi. Gurovi did his crunching and gave us a solution. That was it. There's no decomposition or anything in there. And here are some curves with the different scenarios, things that happen, right? Everything sounds pretty nice. So we said, okay, this sounds promising. So we simulated many different out of sample now cases, use the same policy, right? See what happens. And with what we compare ourselves with actually what people are doing right now on inverters. Inverters, basically what I said before, if you have extra energy, you will store it in the battery until it's full, then you'll sell if you have too much. If you don't have enough, you'll get it first from the battery and then from the network, and that's going to be it, right? That's what inverters right now do. So we compare with that, that's our first result, right? If you compare to that, we get around 11% reduction in cost of this thing working, right? So that's already an impressive thing that you can do. You can reduce the cost of functioning this thing around 10%. You have big bars, especially during sunny days, right? So we have during our summer, you have a larger variance of the decision you can make. In winter, you have much less energy. Basically, the reason of this variability is basically because you have much more energy here than you have here. So that's basically that.
That savings are only for operations or also considering investments in battery?
Only operation. So we're comparing, I have a microgrid with storage, and I just do whatever the inverter is telling me to do. And on the other hand, I have batteries and I have my solar panels, and I'll be doing whatever this optimization model tells me. Now, in both cases, I already invested in the solar panels and the battery. So I'm comparing just operational costs. That's
I don't get why the variability is so high in summer days. If you should expect that the energy is like the cluster was mucho más marcado, with less variability in summer.
It goes back to your question, right? Because you have this chunk of other things that I should show you afterwards, the scenarios that you have for winter, for example. They are much more collapsed to a centroid, right? In the summer, you have this not so small. Think of every other scenario we just put in there is still 13%. So that gives us a little bit of that extra variability we have during summertime. Okay, so that was one part. And I was telling you, well, what if we predict and optimize, right? Maybe we can actually not do this thing of, trying to get the scenarios first and see, how to use them. Because one of the things that we realize here is, sure, I have all this 10 years of data. I'm good to do the clustering, but that clustering doesn't really care how am I using afterwards, right? They're just seeing, what things look similar to what other things. But once you start applying them, you realize that, well, if I have extra energy, you have a little or I have a lot, that's going to make the same decision at the end. If I have extra energy, I'll store it in the battery, for example, right? So it doesn't really matter if I have a little or a lot of extra energy, my decision is going to be the same, right? So maybe what happens is that if I have, two scenarios that are really close to each other, but one is extra energy and the other one is less energy, those are two different decisions, even though they're close by, right? So maybe just clustering things by how geometrically close to each other are might not be a good idea if I'm going to be using this afterwards to actually make decisions. So is there a way where we can actually do sort of a loop where we're trying to create the scenarios at the same time as we are seeing what decisions are being made with those scenarios and try to do that, right? And this is a work did with Elena Garcia. She's a Western master student and the work she did was in this, right? So, of course, we said, there are some techniques where you can do some sort of decomposition on your problem. And we can use that as well, since we wanted to implement this thing in this FunDev project that we had. maybe with some sort of decomposition algorithm, we can actually solve this problem with very little scenarios. And we've actually run it on a Raspberry Pi, so it's very limited in terms of computational capacity. And there's looking around, we found this adaptive partition-based method, which I'm going to be talking to you about, and we can interpret this solution of that as actually something that's optimizing and creating the scenarios at the same time. So let me tell you what's happening. So you have your two-stage optimization problem right there, right? If somehow I'm able to find some sort of values for the variables, right? I'm going to have, since I'm minimizing, I'm going to have an upper bound, right? So whatever feasible solution you give me, it's going to be an upper bound for that. Yeah. I'm going to grab those x from the first stage. I'm going to go in here and see, what are the second stage y's. I'm going to do there, and you can grab all that and have with that an upper bound of the problem, right? Now that I have that, maybe there's a way where I can see all these different scenarios I had, maybe I have millions of those, and maybe I can group them together somehow. In an intelligent way, I can create some sort of partition of different scenarios. I can group them together, and now I have a simpler problem. I don't have those millions of scenarios. I have much less of those, but those scenarios are going to be in there with that, much less requirements in terms of computation. And since I'm grabbing all those scenarios and putting them together, well, I get a lower bound on my optimization problem. So now I have a little bit of a sandwich, right? So maybe I use those solution over there to get a new version of this, a new values of x, and I go back and forth with this. Yeah, that's sort of the main idea of this. I'm gonna grab some x's from the first stage. I'm gonna see what scenarios I get for that. I'm sorry, what y's, values of second stage I'm gonna get for that. And using that, I'm going to see, what scenarios I should be averaging together to create my clusters in this case. Turns out you can prove that if you do this by looking at the dual variables, some additional technical constraints you need in this, but you do that, you actually converge and you get to the optimal solution of this. So that's a very neat solution that Jim Lutke they published in 2015. And Eduardo Moreno and his PhD student, they also used it for other techniques as well for routing problems. So it's an interesting idea because now we can prove by using the dual variables that you can compress everything into really neat scenarios. And actually you're connecting scenarios based on your decisions, not just based on how close they are to each other. Yeah? And furthermore, well, like many other decomposition algorithms, I don't know if you've used ADMN, and there are a bunch of those that they look nice in paper. Well, once you try to use them, since you need to solve a secondary optimization problem, they tend to use a lot of memory, and they tend to be really, really slow. The technique in most of these cases is finding a way to get the solutions of your auxiliary problems really fast.
Just a question to understand exactly what you said. Like you said that this converges to the optimum when you fix the number of scenarios. So that's
what I'm saying is that if you do this back and forth of I get a solution for the first stage, I compute the second stage solution, given that you have a second, everything is going to be separated, right? So I will have a bunch of second stage optimization problems. I solve them all. I get the y's of this, right? I look at them and say, oh, these two should be together, and I just average those. I will end up going back and forth with a partition that tells me, grab all these scenarios and put it into one. Those scenarios, put them into one, and the solution of that problem is going to be exactly the same as the solution of the original huge optimization, two-stage optimization.
For all that clusters, the decisions are the same.
For all that cluster, and that's the key at the back, right? For this whole cluster, things we're considering the 12 variables of this. For the whole cluster, the decision is actually the same, and that's going to be the cool part, right? So you're simplifying and you're trying to create scenarios that make sense from the decision point of view, not just from how close they are to each other.
And then you have bounds on the number of scenarios you need.
No, I can get it. You can get all the way up to the bazillion scenarios you have from the start. Do you have some sort of convergence theorems that I can share with you? And there's some techniques that you can see when you implement it. Things that improve this much further, like not reclustering things. And there's a bunch of things that you can they go out of the theorem, but you can show that it actually improved the convergence, at least in experiments. So yeah, but the key idea here is, if I do this back and forth, I'll be able to separate all these bazillion scenarios I could have I collapse them into specific scenarios that are going to be the ones that represent actually the different decisions I can get, and will have the same optimal solution as the huge original problem I have. So that's the active partition method, right? And you can implement it, you can interpret that solution at the end as, wow, those are the scenarios that should be considered from the start, right? Because I use those in this two-stage optimization problem and actually get the same solution as the original with all the scenarios I wanted to have. As I said before, one of the tricks in most of these decomposition algorithms is able to find a second, an auxiliary problem that's actually easy to solve. If you had to run up Gurobi or whatever you're using as an optimization problem every time, it's going to be super, super expensive. Turns out that in our problem, since we made this decision on how to model the problem, actually the second stage problem is just an algebraic problem. We just see if the price is higher, if the demand is higher or lower than whatever we have there. And the dual variable is actually the selling price or the buying price. So it's super easy to compute, the second stage decisions and see how to group them. That's really fast to do. We could actually do it in a Raspberry Pi, as I said, in a few seconds and do it, and you can solve the optimization problem as well. And the cool thing is, here's an example that we got at the end. For example, this is with invented scenarios. So we created a bunch of scenarios to show, this is just for showing you what's the difference in the two things, right? I created, this is all the historical data you see in yellow points over here. Yeah? If I give it to k-means is going to say, oh, well, these 4 different clusters look pretty similar to each other, so I'll just separate them between them, and that's going to be what k-means does. That's it, right? If you give it to this APM technique at the back, it's going to say, you know what? No. Just grab all these other ones, these big ones, put them together because it's when you have extra energy, and I'm going to be making the same decision for all of those. So grab them together, put them into just a single scenario, and this other one, this little one, that's the one I actually want to have as a different scenario. That makes sense to separate those. And so the clustering for this case, when you do the predict and optimize, is going to be actually this 2 little yellow. I should put a figure line in this one. So are those 2 centroids are going to be the actual scenarios you're going to put in your optimization problem. Yeah? So you'll end up with scenarios that actually make sense from the optimization point of view. And it turns out that you gain a little bit. It's not a huge improvement, but you get around 1-2% extra improvement in your cost by just using these scenarios instead of doing the k-mean thing at the back. You end up with a more robust way of seeing, what are the actual scenarios that you need to take care of, and use that as an implementation in your optimization program. The good thing as well is that you can grab those scenarios and put in your optimization model. You can run in a Raspberry Pi. It's an LP, so it's pretty easy to model and solve. Actually, we were using, you cannot run Gurobi in a Raspberry Pi because the processor is RISC. The other one they need Intel, so we actually use GLPK for solving it. It was pretty easy to do it. So that was probably the thing. Yeah, I'm going to complicate a little things more in the 10 minutes that we have, and that's the question that you had, right? Which, well, now demand is uncertain. What do you do with it, right? And this was the central part of the FONDEF project we had. This was done with Tito Mendemelo from the business school in Adolfo Ibáñez, Gonzalo Ruz, he's in the engineering school at Adolfo Ibáñez, and Carlos Silva, and and Carlos Silva is also in the engineering school at Adolfo Ibáñez, and we're doing this application. So basically the idea here was, maybe you can use machine learning tools as well to do the prediction part. Yeah? And with that prediction part, we have some sort of idea of how things are going to go into the future in terms of demand and solar radiation, and then use the prescription to do this. And that was our FONDEF project with Gonzalo. We did several techniques. I'm going to go into details on how to predict both demand and solar radiation. Right? And now you can think of the error in your prediction as part of your as the stochastic part of your optimization model. And since you're thinking of the prediction as the error, you can separate the error that you have throughout the day. So it's independent 1 hour from the other one. So you're doing predictions in each of the different hours. And the cool thing with that is you can actually use some other decomposition algorithms to solve the optimization problem, which is we use SDTP and the stochastic dual dynamic programming we used for that. Francisco Jara was also in the project, forgot about him. And he was the one actually did all the work. So I was very bad on my part of forgetting his name. Francisco actually was the one that, solved this at a multi-stage stochastic optimization problem using STDP to actually, connect the prediction part with the, decisions that we were taking. And you can also implement, we have an implementation this, actually a real plant that we have in Cauquenes. So we have a bunch of batteries running over there. I can access from my computer to it and send solutions of our optimization problem to actually make it work and use that thing. And here you have the improvements as well. We have around 6-7% of improvement in terms of cost with real data that we were showing, what would have done. This Victor Energy inverters, they had that policy of just, whatever you have extra, you store it. If you don't have enough, you get it from the network. And we compared that to what the optimization problem was telling us, and we improved around 6% the cost of the usage of the energy. So that was the implementation. And for my last minutes before the questions, so we still have a bunch of open questions in this, right? So if we have like variable prices and they're stochastic, how can we put them in? Also, other things that we have when you have continuous distributions. One of the cool things about APM is it can deal with continuous distributions. Right now we have everything clustered into this 48 time steps, but I mean, why 48? Like Jocelyn was saying, you could have much better resolution. If you're using wind, you might be interested in actually having every 10 minutes or less, right? Or even continuous. And APM can deal with that. There's a bunch of technical difficulties for doing that, but that's one way of analyzing this. And also as I said, what happens when you have higher variability, right? Sun is not that terrible. You have other things like a wind, which are much more complicated. So maybe you can use GMM like as technique to actually model this and maybe use that as well as a possible way of modeling uncertainty and put it back into the optimization problem. And in terms of what we're doing now with that, also we're implementing the optimization problem in the cloud and just using Amazon Web Services, solve that there and send the solution only. And then also Cesar, he's a master student that's working with me. We're trying to see if we can model actually the battery. Right? So if you have extra problems of the battery, if you deplete it and charge it very often, you will reduce the life of that battery. Maybe you can put that into your model and try to not do that and reduce the amount of getting in and getting out that you're doing to improve that life. How you can model that? We're doing that with Cesar. And also, consider other objective functions. Maybe you're risk averse. You want to make sure that your battery is at least 70% full all the time, because if you have a shutdown, you will want to have energy there. We are not very used to that in Chile anymore. And when we were little, was here in Chile, we're used to having blackouts. Here now we don't have those. I think the first one was like a month ago. My kids, I remember, they were like, "What's happening?" And it's like, wow, this was common when we were kids. But for them, it's like electricity always comes out of the plug. There's nothing there that can cut it. But anyway, so maybe you want to have in certain rural areas, you might want to have battery charge all the time or something like that. And also integrate rare events into solar prediction. Like you have really bad weather or something like that. We're working with that in this Climat am Sul project with Uruguay and France, and see how to model the stuff of climate problems. And that's it. Any questions?
Can you say something about related work, how other people approach this problematic?
From what we've found, some people are using also dynamic programming as a technique to solve this. I know that Warren Powell at Princeton, they've been some of his PhD students have been working on this. I haven't compared many.
But they use a different model or the same?
No, they use a different. They don't have a variable. They don't. I forget right now what. There was a little bit of a difference in terms of where the variability came from. I think they weren't using variable demand or something in their model. So but it was a sort of the same flavor. That's the closest flavor I've seen from what we're doing.
Then I have a question. I want to know how many batteries I need to buy.
That's an excellent question. One of the things we saw is that once you start doing the sensitivity analysis over your solutions, the size of your storage actually makes a huge difference. So it's an interesting problem because also depends on the cost function. Like we were talking with AgroSuper, and they're interested, they have a completely different cost function. Not just because of the prices, but also because since they're a bigger company and they consume much more energy, they also get a cost by power consumption at certain times of the year. So for them, it's a different model. We were able to do that. I didn't go into details there, but we also were able to model that type of problem. It has a different thing, and you see the sensitivity in terms of the storage they need. It makes a huge difference, which, going back to your question, will make a huge difference in terms of your OPEX, right? I'm sorry, your CAPEX. How much money you're going to be spending in creating this thing? Because if you use this algorithms, maybe you'll want more capacity or even more generation, because this takes advantage of that, and you'll have a lower cost if you do that. Yeah. So now it's part of the sensitivity. The answer to that will be the sensitivity analysis of the decision board. Yeah. Yes.
Rodrigo, related to that, I imagine that it's not so easy. Like, let's have a huge storage capacity and get like load during summer, and then cover the winter with that.
Well,
you don't want that.
Yeah. That's actually, with this type of technology we have right now on batteries, you cannot do that because long-term storage with lead or lithium batteries is not a good idea. But you can think of maybe this green hydrogen thing might be the solution, right? You use that as a storage system. We were talking with Bernardo Valentelli and Tito that you can also use, for example, pumping storage, where you have extra energy, you use it for pumping water to reservoirs, right? And then afterwards you throw the water away so you can generate energy again. Then you have we have to create a second derivative type of constraint to model the inertia of the water in the system and separate it from what you see in the battery. So you can do those sort of things, but it has to be a different type of storage for storing long term. Yeah.
So, but slightly confused on the so you reported an improvement of 11% when you were doing the clustering,
Yes.
but then when you said when you were doing the joint thing, the predict, and you had the improvement of 6%.
2 over that 11.
2 over the 11.
Yes.
Yeah.
In that case, I wasn't comparing with the basic policy. I was comparing with this other method that already was doing really well. So we have 13. Yeah.
Just out of curiosity, do you know if you do this other group that does dynamic programming, this kind of reinforcement learning stuff, do you know what kind of efficiency they achieve? Or
No, we haven't tried much of that. So I mean, anything that can help us reduce the variability of the stochastic part of all the time will actually help us, right? If I knew exactly how much I'm going to be generating and how much I'm going to be spending, that's an actually fairly easy optimization model to solve, right? The complicated part here is actually the uncertain part. So you had any technique that can help us reduce the variability, that's something useful. Yeah. Thank you very much for coming.
Thank you.